the webinar for February. My name is Sue Chrysler. I'm with Texas A&M Transportation Institute. And we're happy to have Tony McDonald and Abhijit Sarkar today talking about a project they recently finished. So you have all come into the meeting muted, and so we'd appreciate it if you would stay muted while they're speaking. You can either raise your hand in Zoom by pressing Alt-Y if you're on a PC, or go to reactions button, or hover over your own face and press the little 3 dots, and there's a way to raise your hand that way too. And Alt-A is for audio, that mutes and unmutes your audio. So enough with the Zoom tips. So let me introduce Dr. Tony McDonald, who's an assistant professor in industrial and systems engineering at Texas A&M University, where he's also the director of the Human Factors and Machine Learning Lab. And his research focuses on integrating human factors methods with machine learning algorithms to develop technology to improve transportation safety and health outcomes. Tony received his master's and PhD in industrial engineering from the University of Wisconsin-Madison, and his bachelor's in mechanical engineering from MIT. Tony was the recipient of the 2019 Human Factors Award for Excellence in Human Factors Research, and just this past fall received the Stephanie Binder Young Professional Award from the Human Factors and Ergonomics Society, and he also currently chairs the Surface Transportation Technical Group of that society. So I will turn it over to Tony.
Thank you very much, Sue. I also want to take the chance to introduce my co-presenter today, Dr. Abhijit Sarkar, who's a research associate at the Center for Truck and Bus Safety at VTTI, and received his PhD from Virginia Tech in 2017. So it's been a great opportunity to work with him and others on this project. Also want to acknowledge and thank Safety for funding this. I think we found some really interesting results, and we're excited to share those with you today. So I think, as Sue mentioned, the primary focus today is going to be on modeling driver behavior during automated vehicle platooning failures. And while many of you may be aware of this, I want to set the stage for what we're doing here a little bit. So first off, as many know, fatal crashes are happening at an astounding rate, and they're alarmingly stable for where we should be and where we think we may be with technology. There is some promise in the form of results from testing of automated emergency braking and forward collision warnings on roadways, which have decreased certain types of crashes by as much as 50%. So there seems to be an avenue here that additional automation can continue to reduce these fatalities and add to these numbers, but also reduce things like transportation costs in general. So the natural question there is, then what is holding automation back? And of course, there are some limitations associated with computer vision and sensors and algorithms, and they're continuing to be developed. There's also some high-profile crashes that have happened and been well publicized that have eroded public trust. And then there's some limitations with policies in terms of supporting the broad deployment and the infrastructure development needed for success of these systems. But even with all that as a backdrop, I think the most prominent reason is that AVs are just fundamentally not designed to interact with humans. So what do I mean when I say that? So I really like this depiction. It's from Victoria Banks and Neville Stanton, a recent paper in Theoretical Issues in Ergonomic Science. So what you see here is a network of the actions that a driver has to undertake in driving a manual vehicle on the left-hand side, and then an automated vehicle on the right-hand side, and then how they will transition between these in the network. And so what you see immediately is that you may think that the automation should be sort of a more sparse network with fewer tasks, but it's actually much more dense, and there's actually even more tasks. And the reason behind that is that we're not just simply taking drivers out of the equation, we're actually asking them to monitor all the systems that they would control before, and in addition, be prepared to take back control when necessary. And what's more striking is when we look at that next to things like product names, like the autopilot, for example, autopilot, at least to me, doesn't conjure the need to have this sort of dense network of responsibilities. So that's where this disconnect is happening. And we'll propose in this talk that we can address that by developing driver models. And the way that these fit into this sort of design ecosystem of automated vehicles is that we combine driver models with pre-crash kinematic data. So these are things that we've observed on the roadways in certain scenarios. And then also prototype automated vehicle algorithms. And then we can make from that combination safety predictions about what we think will happen. And we can use those safety predictions to tune the automated vehicle algorithms back within the abilities of human drivers. And so we're not putting them in a state where they're not able to respond safely to failures. To develop driver models, we can frame this as a series of 6 steps. The first one is identify a scenario, then selecting a framework, collecting data, training the model, comparing the model predictions with experimental results, and then finally using the model to predict new data. For this project, we focused on identifying scenarios based on current things that were happening on the roadway, so observations that we had seen. And specifically, what we did is we conducted a probabilistic topic modeling analysis of the California DMV's automated crash report database. So any vehicle with automation that's being tested on the roadways in California, if it gets into a crash, you must file a report that gets logged in this database. And at the time of our analysis, the database included about 114 crash reports. And what's unique about these and important is that they actually contain a narrative crash description about what happened in this particular scenario. So this data is really rich in the sense that it is actual crash data. It's what's happening on the roadways. And these narratives are relatively detailed descriptions. There's some limits here in terms of that these are test vehicles, so the technology is developing over time, and it's a limited range. All the crashes happen in the San Francisco Bay Area, and it's somewhat of a small data set for probabilistic topic modeling. But again, we're using this to really sort of scope down what scenarios are important for us to look at. So the way that topic modeling works is it's actually a method of fitting 3 different types of distributions to a data set, including terms and documents. So the way you can think about this in a crash sense is each crash narrative is a document, and then the terms within that are the description of the crash. And then our goal here is to identify topics or themes across those data sets. And our hypothesis is that those topics or themes will actually align with scenarios of interest. So to do topic modeling, we do some pre-processing on the data. This is mainly just removing common terms that might kind of distract the model. Then you need to select the number of topics, which you can do with a sensitivity analysis, fitting the model, and then analyzing the distributions that you get out. And the 2 that are most interesting are this crash topic distribution and the term topic distribution. So this is showing our results here for this database analysis. We found 5 topics in the database. And so you're seeing the topics on the x-axis, and then each narrative is on the y-axis. And we've additionally grouped this data into 3 separate sections. The top plot here is crashes that happened during or after a transition of control from the automation to the human driver. The middle is showing when the autonomous vehicle was in motion and got into a collision. And then the bottom chart there is showing when the autonomous vehicle was stopped, or the vehicle was in autonomous mode and stopped. And of course, when we looked at the data set, we see that there's a high frequency of crashes where the autonomous vehicle was stopped. Those are mainly captured in topics 2 and 3 and 5. But topics 1 and 4 are a little bit more interesting. So topic 1 is mainly all the transition crashes, or almost all of them, were highly represented in topic 1, which means that the transitions are actually a topic or a theme in this database. There's a lot of crashes happening during these transitions. And then topic 4 is showing high prevalence in the autonomous moving case. We can get a little bit more insight into this then by looking at the term and topic distribution. So these are the terms that are strongly associated. And if you remember with topic 1, our hypothesis was that this was related to transitions. And in fact, we see terms like manual and control here to indicate a transition of control. And so it's sort of confirms that hypothesis. We're also seeing a high prevalence in topic 1, but also topic 4 of where the collisions are happening in terms of places on the vehicle, and then some roadway items as well, like intersections, clipped and overtakes. So when we look at this, then what we can take away is first that we need to have a focus in our modeling of transitions of control. Transitions are a clear theme in the database. Of course, as I mentioned, the majority of crashes are involving the AV being struck from behind while stopped. This is something we're not so focused on right now. From a sort of liability standpoint, most of these are not the fault of the AV. Maybe something that could be done in the future, but sort of beyond the scope of what we're talking about here. And then finally, intersections, turns, and overtakes, more importantly, appeared in multiple themes. So based on this, we decided to focus this project on transitions of control, and then also specifically overtaking and braking events. And you'll see that emerge later on. That brings us to selecting a framework, and we did that through a literature review. Now, this has been published in Human Factors Journal, and we have a citation here at the end if you're interested. But we reviewed about 250 AV studies. We found that the factors that significantly affected takeover performance included takeover time budget. So this is how long you had to respond before a crash would happen. Handheld secondary tasks, repeated takeovers, so practice of the takeovers, silent failures, and then driver factors like fatigue and alcohol, among a few other minor factors as well. This takeover time budget, takeover time relationship was one of the strongest effect sizes that we observed, and it's something that will be quite important when we come to the next sections of this in terms of helping us kind of decide on a modeling framework. And then we also found that studies suggested that the drivers responded similarly between manual emergencies and AV takeovers. And this link is really important because it suggests that we could use models from manual emergencies and try to have those generalize to AV takeovers. And in fact, that's sort of the strategy that we employed for selecting our framework. And then finally, this is somewhat related to the takeover time budget issue, but there's a common thread of visual looming based approaches across all the different components of a takeover or an emergency response. And so we decided to focus specifically on models that included a visual looming based component. Now, we also identified and broke down the takeover process to a series of kind of discrete steps. Now, this is a bit of a simplification. I think there's some nuance that we could discuss with this, but for the purposes of the modeling, we felt that the takeover breaks down into a period of action selection and then cognitive readiness, and then also an action execution and sort of evaluation phase and the sort of perception action loop. So when we map that to modeling frameworks, we decided to focus on the random forest decision model for action selection, and then a visual looming based evidence accumulation model for cognitive readiness and takeover time, and then piecewise linear model for braking control, and a open loop control model for steering control. And so we're going to talk about these together. At this point, we're going to sort of walk through the rest of the process first for the random forest decision model because of the focus of data we had there. And then we'll talk about the last three after that. So as I hinted at here, the next step is to collect data. And for the action selection component, we focused on SHARP2 data. So I'm going to pass this over to Abhijit. He led this portion of the project. And so Abhijit, you should have control now and you can take over.
Okay, thank you, Tony, for the introduction. I'll just quickly check if I... Okay. Yeah. So as Tony mentioned, that we wanted to look at how driver reacts, and means how that depends, how their reaction is a function of multiple intrinsic and extrinsic factors, and that can include what are the situation, the driving situation is, what the exact escalation of the situation that they are into, and how they are reacting to just before that escalation, how they were reacting and how they were behaving in terms of their visual attention and in terms of their braking patterns. So for that, we looked at SHARP2 NDS data, which is one of the largest naturalistic data collected. And it has around 3,000 participants and 40 million miles of naturalistic data. We specifically chose 355 rear end crashes and near crashes. And means we selected them with some specific operating conditions. That means their operating conditions at the start of the event that should be greater than 15 miles per hour. They are all light vehicle events, so means all the conflicts are between one light vehicle to another light vehicle. And definitely we have performed manual reduction on all of these data. So these manual reductions involve to understand that what exactly the situation was just before they even started. So how much is their last glance eccentricity is in terms of their horizontal eccentricity and vertical eccentricity. Also, like if they are paying enough attention to the road, if there is at all any escape path feasible, and if there is any escape path feasible, are they having any escape glance just before that event? And also in case that they are looking outside and not looking forward, uh, are they looking inside or they are looking outside? On top of that, we have added two more, which are like driver impairment and secondary behaviors. And with all of these, we want to understand that whether they will finally steer away from that lane to a separate lane, or they will apply their brake. So these are the main two components for us. But before that, we have introduced in this work several new variables. And all these variables mainly pertains to the visual behavior or the attention of the drivers. In this image particularly, means we define that a visual cue onset point is somewhere where if they were looking away, then the point that their gauge comes to forward, that's the VCOP is. On the other side, if they are not looking forward and the inverse TTC value that crosses 0.1, then we define that as the VCOP point. Now, definitely for that, we have added few more variables, which is like that add VCOP, generally what is there in inverse TTC. For eyes off-road cases, that value is 0.1, but in eyes on-road cases, the value is 0.1, but for eyes off-road cases, that value varies. And similarly, how is their inverse TTC when they first realize that there is something happening? How was their last glance eccentricity? If we combine the horizontal and vertical eccentricity, how much was there? And also another thing is that how long they were actually looking at the road or scanning the road before they reach that VCOP point. So these are the all new variables that we looked at. And this is one visual representation that how a typical near crash scenario actually looks like. So you can see that this is a special case of two vehicles being there, and means immediately the host vehicle realizes that the vehicle in front of them, which is shown in gray color, it is braking very heavily, and that's why its inverse TTC value is escalating, and means it is becoming really safety critical. And at that point, they decide to have either they have a physical reaction, and then after that, they decide to have a brake or a steering action. Now, we looked at it in another particular framework, which is like how people look to take their glance away from road depending on the criticality of the event. And there we try to find out that when they look away the first time, what was the inverse TTC value? And then how long they tend to look. And we really find out that if there is, if the inverse TTC value is much lower, they feel really safe and they actually engage in much higher glance to higher off-road glance. Now, with all this taken together, we have run a random forest model. And as Tony mentioned, that means this is a very nonlinear system. And means to incorporate the nonlinear behavior of all the variables, we thought that the random forest decision-making process are most effective for this. We have also run a linear model of logistic regression just to compare this. But For this, we really find that after doing a 70% data using for training and 30% for testing, we find that with random forest model with a inverse threshold of 0.1, we can get a very good accuracy of almost 96%. Now, we have tested for two different thresholds because in literature, 0.1 and 0.2, both are used interchangeably, and both defines a particular case. Now, what this implies is that 0.1 TTC means that their time to collision is 10 seconds. So we show that even 10 seconds, if we look at their behavior, 10 seconds before the actual criticality value, we can still have enough information so that we can predict whether they will be braking or they will be steering. Now, when we look at that which variables particularly played role into this, we see that the top 6 variables are the physical reaction. When they have the physical reaction, that decides whether they are going to brake or steer. And at the same time, if there is an escape path feasible. Now, this may be a very intuitive or generic knowledge, but still we saw that means that plays a role in them. And also how long they are looking at the road, what is their last glance duration, and how much they are looking away from road. This all play very vital role in there. Now, when we look at in more details, I want to specifically focus on the right side, is that this eyes of threat that actually plays a very good indicator for all the eyes of threat events. It is a very good indicator that after a value of around 50 to 60 degree gaze eccentricity, they tend to have a more steering actions rather than a braking action. So as a conclusion, we find that means we can develop a maneuver prediction algorithm by looking 10 seconds before that. We introduce 6 new variables that plays very important role in this. We can get a very good accuracy of 96%. And also time to collision value, the physical reaction and visual cue on point, they have the strongest influence in the decision making. It's more or less said that how well the driver is prepared to take any action. Back to you, Tony.
Thanks, Abhijit. So we got some, as Abhijit mentioned, some critical insights from the SHARP2 data set in terms of action selection. We believe from our review those could translate. But one of the limitations of SHARP2, or at least the portion that we were looking at, is it doesn't actually include automation. And so to supplement that, we included conducted a driving simulation study, and we used that to parameterize the rest of our takeover component models. And so the simulation study was conducted at TTI's RTI driving simulation lab. We had 64 participants in it, 32 males and 32 females, between 19 and 64 years of age, with a mean age of about 41 and a half. The study itself was a 2x2 design that included within participants factors of scenario type and scenario criticality, and then included between participants factors of alert and failure type. So some participants experienced a silent failure, others got an alert, and then each driver drove the 4 drives corresponding to the different combinations of the within subjects factors in a counterbalanced order. So we took the data from that study and we started to train our models. But before I do that, I just want to introduce this idea of visual looming that I mentioned before. So if you've read in depth on the research in driver modeling and especially braking behavior, you may have seen this term. Visual looming is sometimes described as what's called inverse tau, which is the ratio of the rate of expansion of a forward vehicle in your forward view over the angle itself. And if that math doesn't quite connect with you, I have a quick demonstration. So if everybody can stare at their screen, this is what it looks like. So that's the effect of visual looming. It's this expansion, and that's really what drives a lot of braking behavior. and also just generally human responses to sort of objects looming in the forward view. The other part of the model that's critical to understand is the idea of evidence accumulation. And the way I like to think about evidence accumulation is to go back to my introductory chemistry class where we were talking about chemical reactions. And so when we talked about that, we had this idea that there's this thing called activation energy. And once you reach a threshold with that, you sort of trip that, and then all of a sudden the reaction would happen and you'd get the desired outcome. So evidence accumulation works very similar to this process, but instead of activation energy, what we're looking at is evidence. And when I say evidence, what I mean is evidence of the need to break, which is, as I said, most strongly been related to this idea of visual looming. And sometimes in an automated vehicle context, we actually talk about this in terms of looming error, which means the difference between actual and expected looming. So if you expect that the automation is going to be working, your looming would be different. But in our case, that expected looming was 0 because of the automation. So it's just also just the visual looming in this case. And then we didn't look at this specifically in the simulator study, but often brake light activation is included as well. So these are, as these engage, and as you see a brake light come on and you get this visual looming evidence, once you reach a threshold that is usually kind of self-defined in these models, then you will apply the brakes. And that is governed by weights associated with this evidence. So for our takeover time models, we focused on that evidence accumulation, and then we compared it to a log normal distribution. So this is sort of the traditional method of predicting braking response times. So it gives us a good baseline to compare against. And then we also, as I mentioned, looked at a braking control model, which was just a piecewise linear. So I'm not going to go through specifics of the equation here, but you can see it. And then for avoidance steering, we did a comparison between two different types of models. One is an open loop control model, and the other is a more traditional closed loop. So if you've seen the model from Salvucci and Gray from 2004, that was our baseline model here. It's a 2-point model of steering control. So we trained the models on half of the data set and tested on the other half. The one exception to this, and why there's an asterisk, is that we actually, for the evidence accumulation model, we're doing some comparisons across the distribution. So we trained and tested on the whole data set, although that's something that we're looking into expanding on. To find parameters and weights, as I hinted at, we did a grid search over a parameter space, which was governed by previous models. And then we used KL divergence to assess the quality of the takeover time models and root mean squared error to identify the best models for the braking and steering control. So after we went through that process, then we get to the step of comparing model predictions and experimental results. And so this is showing the takeover time results. So this is prediction of the takeover time. On the right-hand side, we see the evidence accumulation model, and the left-hand side, we see the baseline log normal model, and then the experiment is gray. On the top, we see a cumulative distribution function, and then the bottom, we see an estimated density function here. And both models do a reasonably good job of comparing or replicating the experimental data. But as you can see, actually, the evidence accumulation model does a little bit better job and is an improvement off of the log normal model. Now, from braking control standpoint, we also saw some positive results, but some things that were a little bit more complex. And when we looked at this in more detail, we realized that this actually broke down by the critical and non-critical case. So I mentioned before that this scenario criticality, so this gets into how long drivers had to respond to a particular crash or a particular event. So in the critical case, a single piecewise linear function did a reasonably good job of replicating the behavior, and you can see 2 examples of that on the right. And then on the left, you see 2 examples of the non-critical case where our performance was not quite as promising. And one thing you can see from this is that pattern-wise, it looks like it does capture the behavior quite well. It's just that these drivers had sort of a tentative initial brake and a few other responses as they were sort of refining their control. So something we're going to explore in future work is looking at expanding beyond just a single piecewise prediction into something that's a little bit more complex and also driven by the findings of the looming model. And then in terms of avoidance steering, as I mentioned, we had this comparison between a sort of more traditional closed loop approach and an open loop approach. And we found for that the open loop model was in particular much better at capturing avoidance steering than the baseline closed loop model. And you see the overall results there at the bottom. And then some examples of good fits on the left and sort of less promising fits on the right-hand side. Now, this isn't unexpected. We found that open loop models especially have been growing, and there's been some broad comparative analyses that have shown that open loop models generally do a little bit better job capturing avoidance steering than something like closed loop. And that idea has been around for a long time, but it's good to see that that also translates to this space as well. So to summarize the findings from this component of the project, we see that evidence accumulation models of braking reaction time perform better than the reaction time distribution model, and that piecewise linear models do a reasonably good job of predicting critical braking behavior well, but maybe are a little bit more limited or a little bit more complex in the non-critical scenarios. And then open loop models predicted avoidance steering slightly better than the closed loop models. But as I mentioned here, there's sort of a disconnect. If you think back to the components of what I talked about of things that were important to take over time, and then the things that we covered in the models, we did a good job of covering this takeover time budget through the inclusion of visual looming, but we haven't really looked at driver states. And then one sort of maybe even glaring contrast is in the random forest decision-making model, we saw that there was a really critical role for gaze eccentricity, and we didn't include that here. And specifically, the reason was because just the way that we set up the simulator, there's not a lot of additional things to look at, and especially in a quarter cab simulator. And so what we've been doing more recently is exploring this role of gaze eccentricity in evidence accumulation models. And that's sort of kind of where we've ended the project and our launching off point for the next phase. So I'm actually going to pass it back to Abhijit to talk about some of our latest results that are hot off the presses with that. So Abhijit, back to you.
Thank you. Okay. So as Tony said, that the gauge eccentricity and means how much we look at the road, that has an impact on how much information that we are gathering, and that evidence that can happen. So definitely when we are looking at the road, it's assumed that means we are scanning the road, but at the same time when we are looking away, how much information that we are gathering by our peripheral view. That is something we wanted to understand through this work, and that's where we particularly looked at this model in a two different accumulation based work. Number one is that the visual looming that Tony mentioned, and another work that is going in parallel, and that has been for a long period of time, that we believe that the brake light onset time, and that makes a driver aware, and that accumulation information also plays a very critical role. Now what we have done here is that we made this weight, that how they accumulate this is a dynamic weight. So you can see that it is time varying rather than it is a constant values that the traditional models use. So going from there, what we use is that particular value takes one certain value when they are eyes on road, but at the same time they have a fraction of that accumulation when the eyes are off road, and the same thing happens for the brake light as well. But in the process, we have tried out several different ways, and the one thing that we wanted to see that how one variable particularly we have used is their yaw. So you can use yaw, roll, pitch, yaw, all three of their gauge eccentricity values, but at this point we have specifically focused on the yaw value and tried to model them in a way that means if they model them in two different ways. Number one is that they will increase linearly with the gauge angle, or they will have exponential. Now for the exponential, it's like that there are several evidence in literature that how we look at certain things in our peripheral views, they sometimes follow a pattern like this. So that's why we try to replicate that in a more traditional way. But another thing is that if you look at this, that the more nearer that they have comparatively a different value for this. So their accumulation patterns are different, and the same thing we have tried to do for the break onset as well, but here we have used a step function specifically. Now, as a result, we have total of six models that we have tested, and if we look at this for these, then number 1 and number 4, they are the baseline models where we only have the accumulation from the looming in model 1 and only have accumulation from the brake light in model 4. And the others, they actually is a combination of that. And also another thing is that the accumulation start point for model 1 and model 4 is only when they look back to the road, rather than when they are already having already in the during their last glance, they are not accumulating any evidence. On the contrary, 2, 3, 5, and 6, they can start accumulating the evidence starting from the tau th point. So next we show that if we look at this particular scenario and that eyes on and eyes off thread, we can clearly see that we can so we have modeled 2 different rate of accumulation, and ideally when the red line crosses the black line, that's where a driver is supposed to activate their braking or steering. In this particular case, we have used braking, and total of 99 such events where the eyes off-road cases were there, we have only used them. Now for the model performance, when we first look at the model 1 and model 4, which are our 2 baseline models, they doesn't match very well, and they have a RMSE error of around 0.9 seconds. But in contrary, when we look at the other models specifically, then we see that which are just adding the exponential model to model 1 and model 4, we see that their patterns matches much closer, and the error almost halves. So 0.5 second is the total error that we receive. One interesting thing I want to identify here is that for both of them, even if the value of the RMSE, they are 0.5 seconds apart, but the distributions particularly is much different in both the 2 scenarios. And that's why we find that adding the information of peripheral view and the accumulation, evidence accumulation during the peripheral view plays a major role. Now, the next question we asked is that, so between model 2 and model 3, if we compare model 2 and model 3, where the accumulation is linear and exponential, which one performs better? They kind of performed very similar in terms of the RMSE value and also in terms of the KL divergence. And interestingly, they look very similar in terms of their behavior. But one other thing that we did was to do a cross validation for all these models. So we needed to know that if, as we are doing the number of parameter fitting, if they are ultimately overfitting and means they cannot generalize this. So that's why we used 66 events for training and 33 events for testing. And we realized that model 2, which has the linear accumulation, they actually generalize better than the model that has the exponential. For both model 3 and model 6, we see that that number is between training and testing, we have a comparatively higher gap of almost 1 second. So in conclusion, we showed through experiment that driver accumulate evidence even before that particular VCOP point, or when they look forward, the instance that they look forward, they still have the accumulation gained. And definitely linear model or exponential model of the glance accumulation performs very similar, but linear model generalizes well. Now, with all these kind of models, we still have a lot more experiment to do, and there's lots of questions we can ask here, that how effective, if they are very much situation dependent or they are general for all the cases. what kind of weights that we can assign to braking accumulation as brake light accumulation compared to the looming accumulation. But those are probably some questions that we will be working on in future.
Okay, so looking across all of these modeling approaches, I think one of the things that comes out is that most of what we presented here today generally reflects what drivers were doing quite well. So from a decision-making standpoint, we found strong evidence that the random forest adequately replicated driver decision-making. We found some positive evidence that the evidence accumulation models, particularly those that include gaze eccentricity, replicate driver behavior well. And then also piecewise linear and open loop steering control models replicate the behavior quite adequately as well. We did see, at least in the braking models, that model fits declined in non-critical takeover scenarios. This is something that I think we need to look at in future work. One of the interesting things here is that when you look at data from, say, Sharp 2, and you do filtering on it, a lot of that filtering based on time to collision numbers doesn't necessarily incorporate the same data we had from the simulator study with these non-critical scenarios, because by definition, they're not critical. And so if you expanded the threshold in Sharp 2 in terms of a data search, your amount of data that you'd be looking at would grow exponentially. So I think it's something that may be a gap in some of the translation of models trained on manual emergencies to this automated space. And so these non-critical scenarios warrant some additional attention. And then also, as we saw in the last part there, gaze eccentricity plays a significant role in driver responses. We can't necessarily disregard that looming evidence that accumulates even when someone isn't looking directly straight ahead. I did want to touch, just in case there's anyone who's either a student or faculty or someone who may teach a course in this that's interested, that we also produce some educational materials from this project. We have a lecture module on driver modeling. We actually have two versions of that. One is just a one-day sort of 45-minute lecture, and then the other one is a 2-week 4-different lecture version. And we're happy to share those materials with anyone who's interested. We also, as a part of this project, developed an R-based visual looming modeling activity, and we can share the baseline code for that. It's a project where students actually fill in R code and do some predictions of their own and get to test out and experience what these visual looming models look like. And then we will, at some point in the near future, release our final modeling software, so that can be shared as well. That will be shared through my lab's website. And of course, we would be remiss if we did not acknowledge the contributions of both the students in my lab, the Human Factors and Machine Learning Lab, particularly my student Hanana Alambegi, who was really critical in developing the simulator and conducting the simulator study, and is doing most of the analysis with the driver modeling on our side. And then from the VTTI side, Jeff Hickman, who's been sort of a co-lead with Abhijit on that side, and Johan Engström as well, who's now at Waymo, and then Wenyan and Tobias, who were students that worked on this project. And then finally, last but certainly not least, Dr. Gustav Markula from Leeds in the UK, who's been sort of our sort of senior technical expert on this, consulting with us on the various steps and decisions in the project, and really integral to our success. So with that, thank you so much for your time and for your attention in attending this today. We're not open it up to questions now, and I will highlight here that we've showed all of the stuff we talked about today is either been published or in the process of that. So the first two should be accessible on ResearchGate, and then the last two here are the decision-making work, which we just got accepted to accident analysis and prevention, and that should be out in the next couple of weeks. And then a final paper on the simulator study, which is hopefully going to appear shortly in Human Factors as well. And as always, you can contact us if you are looking for pointers to these publications. So with that, thank you very much, and we'll open it for questions.
You can go ahead and unmute or raise your hand if you have a question. But while you're thinking of your question, I have a question. You talk about why you chose braking instead of throttle release, or did you consider throttle release? I mean, there's some evidence that people Dan McGee, he calls it the waggling foot of indecision, that you take your foot off the gas, but you haven't quite hit the brakes. That might be a more earlier indication of response.
That's a good question. We did not look at that in the modeling, just because I think the way we were conceptualizing it was that sort of process would be encapsulated in the evidence accumulation, and then at the exit of the evidence accumulation decision stage would be like, that's the point where you've already done the physical shift of the foot to the brake, and then you're just kind of doing the braking control. But I think that's something that we need to look at with the simulator study, especially because we looked at the braking control, but we have that data, but we haven't analyzed it yet. I agree with you, Sue. I think that would be a really interesting dependent measure to analyze.
Yeah, I mean, I think the same model and parameters would work. You just gotta, I mean, some of it, you know, the sensitivity of throttle release is it's not as clear cut as braking. So depending on how sensitive your actual physical pedal was. So, you have other questions?
I have a question in the chat. I will just answer that. So I was asked that if the driving is manual. So yes, all the SHARP2 data, they are human drivers. So all the drivings are manual driving. Nothing is automated driving. Yeah, all the work that being presented using the SHARP2 data.
Can you talk a little bit more about how the review of the California DMV crash reports? I mean, I could see how they tied to like how you identified SHARP2 data, but did they inform your driving simulator scenario selection at all?
Yes, yeah, I think I went through that a little quickly, but the two different types of failure scenarios we focused on were, the first one was an overtaking scenario where there was a stalled vehicle in the lane ahead that was exposed after the lead vehicle departed the lane. So that overtake situation was one where we saw a lot of issues in the autonomous vehicle crash database. And then the other scenario was a braking scenario where you're driving in a platoon and the lead vehicle presses the brakes, but it doesn't get recognized by the participant's vehicle, and then they have to manually respond. That one is a little less informed by the database, but I think just looking at sort of some possible failure modes and things like that, that was another one that kind of seemed to emerge. So I think the focus on the transition especially, and then this overtaking scenario is sort of what we pulled out of the database.
Okay. Anybody else have any questions?
Go
ahead.
I see a question from Dina, but so did you consider both daytime and nighttime driving? Yes, we have both driving included here.
I mean, I think that's an interesting question. Just, I think the brake light's a more salient cue at night. I mean, when you have a fairly impoverished looming cue at night. So.
Yeah, that's true.
All right. Well, there's one more in the chat. If you want to look at that one, Tony.
So for random forest, we started to work with more traditional models, and random forest generally works very good in terms of in this kind of diverse data, if I say. And that was the one major reason that we chose random forest. And again, it is a more of a decision-based model, and we had like the binary variable as well as the continuous variable. So just bringing all of them together, we believe that traditional methods like random forest will be good. But you are right that there are many other time series based prediction methods, and that can definitely be used in this.
Going once. I'm going to mute so you don't listen to my phone ring. Okay. Well, so tune in March 25th for our next webinar, which is looking at the use of crowdsourced data for estimating traffic volume to calculate safety performance functions for low volume roads. And there's information on that on the safety website, and you can sign up the same way you did here, and it will get posted on the US DOT webinar listing as well. So thanks to our speakers, and that's all. Have a good day.
Thank you, everyone. Thanks, Sue and Eric, for organizing. Really appreciate it.
Yeah, thank you very much. Bye.
Bye.